Okay, good morning everyone. For those of you who don't know Christos is the assistant facility manager here and he's involved with lots of training. And having had a sneak preview of his talk the other day, it will be almost as if we were at the microscope with Christos. So Christos.
Okay, thank you, Shores. So I'm hoping my talk will be more a visual appreciation of what you do when you go to the microscope to collect data, and not that many formulas. I think I have one, but that's about it. So the outline of the talk is we're going to talk about aligning the microscope before you collect data, how to choose a microscope, whether that's for screening or for data collection, choosing a detector that will collect with your microscope, how to check the grids initially, make sure you find the right areas for your data collection. Then what choices do you have? How do you collect the data? We'll talk about the software that's available. And we'll mostly concentrate on what we use here at the LMB. And so generally when we want to collect data, we have a sort of generic procedure. We go to the microscope, we load our samples, we then align the microscope. Next step, find a suitable grid, and then we set up data collection. I think this is pretty much how everybody collects data. So before I talk to you about microscope alignments, I'm just going to revisit a little bit on what Chris said about the microscope and the different parts, so that you can appreciate which part we're moving when we do a certain alignment. So Chris talked about the gun, which is very important. I'm going to mention it again. You can have a choice of a thermionic or a field emission source. You have two condenser lenses. Condenser lens 1 affects the magnification of your source, and it's generally called the spot size on your microscope. The second condenser lens will control the diameter of your beam, so the spread of the beam on your specimen, and it's usually the intensity or brightness knob if you have a different type of microscope. And together C1 and C2 control the dose on your specimen very accurately, so you can choose a dose and a diameter that fits your experiment. In addition, we have deflection coils in the microscope. Now, although mechanically all the lenses are put onto the microscope and assembled so that they're kind of line up, we still have to shift the beam and tilt it around in certain places. So we have these deflection coils, which you can think of as mirrors for light microscopy, which will bend the beam and shift it in different places. So we have some of these coils near the gun, which are called the gun alignment coils. We have some just before the sample. These are called the beam deflection coils. And we also have some before the image is projected. These are called the image deflection coils. So we also have certain elements called stigmators. Sorry, moved away. The projection, intermediate and projection lenses affect your magnification. That will be the magnification knob on your control panel. And then the stigmators, which affect the symmetry of your lenses. Because the lenses are not perfectly symmetric, we have to make them round using these stigmators, which are built into the lenses. We'll talk about that a little bit more. Right, so the basic steps, and basically we're fine-tuning the alignments. The whole column alignments are done by the engineer at the installation, and then occasionally your facility manager will run through and make sure things are not moving too much. But from day to day, there is not a huge change in the alignments because the optics are fairly stable these days, especially on a microscope such as the Cryos. But we tweak the alignments and we do a few steps. A gun alignment, which is, again, fairly stable on effect. We don't really need to do this every time. We center our C2 aperture, so the aperture just below the second condenser lens. We adjust the beam tilt, which is important for high resolution. And then we insert and adjust our objective aperture. We remove any astigmatism in the condenser and objective lenses. And if needed, we do a gain reference for our detector. And if you're using an energy filter, we go along and tune that as well. So this is the general procedure that we follow. So starting at the top, a gun alignment. What do we actually do here? So we're using where the red arrow points, we're using the gun deflectors to tilt and shift the beam off the gun so that it lines up with our condenser lenses. So on the left scenario here, we have a gun that is going down the column, but it's shifted in relation to our first condenser lens. So this requires a gun shift, needs to move over a bit. In the second scenario in the middle, we have a tilt in the gun, even though it's more or less centered. So here, we would lose brightness because the electrons would be shooting on the side rather than going through our condenser system. So we have to adjust the tilt. And then when everything is perfectly centered, you will have this scenario here where the beam is going down the optical axis of your microscope and is centered. Now, one thing I forgot to mention is that all the alignments are done in respect to an optical axis, which is the center of your screen or the detector. So we assume that is the center of our optical axis, and we try and get everything lined up with that screen. So we check for maximum brightness. That will be the gun tilt, and we make sure that the beam is centered when we have a weak condenser 1 lens, when you have a small spot size. Then we center our C2 aperture, which is just below this second condenser lens. This is just a mechanical adjustment of the aperture to make sure that the beam goes to the center. And if this is not aligned, what you will notice is when you spread the beam will shift to one side. And if you go over focus and under focus with your intensity knob, it will move from either side. At the end, you should have a perfectly centered aperture. When you expand the beam, it will expand concentrically with your screen. And we're going to show you how to do that in a bit. Next step is to check the condenser astigmatism. Astigmatism in general is a property of the lens, which is the perpendicular directions don't have the same strength, so you get 2 focal points shown here. And how this manifests itself on the condenser lenses is that because the distances here are different to the distances here because of the 2 different crossover points, you will get an oval-shaped beam, which is astigmatic. So the idea is to go from something that looks oval into something that is nice and round. And to do this, we adjust the condenser stigmator here. So a very important alignment that we do is beam tilt correction. So this is making sure that a beam goes down the optical axis of the objective lens. So there is 2 ways to correct for this. There's a sort of a rough way, which is called the rotation center, and then a more accurate way if you're doing high-resolution work, which is called the coma-free alignment. So here's a diagram which explains what we're doing when we do a rotation center. So when you click in your alignments and you click on the button rotation center, what the microscope does, it takes the objective lens and it starts wobbling the strength of the objective lens. In essence, you're going under focus, over focus, under focus, over focus, and it's wobbling all the time. So imagine 3 points there, A, B, and C on your object. And as you can see, the beam is not going parallel to the optical axis, it's tilted. Now, at one focus setting, you will have the back focal plane, that's where the beam will converge, and you will get an image on your screen. Now notice that the ray coming from point B is going through the center of the lens, so it doesn't change its direction. So coming from B, it goes to B, and because it's going through the center of the lens, it's actually not changing direction. Now, if we change the focus on the lens, we have a new focal plane, and you'll have a new A spot and a new C spot, but because, again, B is going through the center of the lens, is not changing position. So, but how can you tell that you've got a tilted beam? As you change focus, you're changing the focal planes, so the positions are moving here, but because of the helical path of the electrons, so as they move, they go in a spiral path. When you change focus, the focal plane, they're also rotating, they're changing position. So they're going here, then they're moving in a helical path. So actually what will happen is you don't just get a movement of these points, but you get a rotation here and here. And it'll be, the rotation center will be where the beam passes without being altered. So when you do the rotation center alignment, you try and shift this point B into the center of your screen, because that means then that your beam is going down the center of the optical axis. And what you should see is that something that's in the middle of your screen will stay centered, and things on the edge of your screen will rotate a little bit. So this is what you do when you adjust the rotation center. Now this is a sort of a rough alignment, and it's good for medium resolution work. Sometimes you can get it quite accurate, but it was figured out that this wasn't sufficient for high resolution work. So the next step to do this, and just to remind you what you're changing here when you change the beam tilt, you're using the beam deflection coils to change the beam tilt. That's what you're doing. In the next step, you're doing the same thing. You're changing the beam tilt again. You're just doing it a different way. The microscope sets up the conditions a different way. So what we have here, we have this panel A is if you have a beam tilt, and panel B is if you don't have beam tilt, if it's going down the optical axis. So imagine you have beam tilt, right? And then what the microscope does, from that original beam direction, it tilts a little bit plus and a little bit negative, and it keeps doing this. Now, if you're not going down the optical axis, those two images will have a different focus. And that's what you see here. With the white arrows, you have a tilt along the y-axis, plus and minus 5 millirads. And you can see from the ring shape that those two FFTs look different. So that means the focus is different when you tilt in the y direction. The same thing along the x-axis. Those two images are different. It means that we're not getting two symmetric images because the beam is not going down the optical axis. Now, if I tilt the beam so that I'm going down the optical axis and then start tilting plus and minus, those two images now are symmetric. They will have the same focus values, and we end up with a situation here where the opposite beam tilts give us an image with the same defocus and the same in the other direction. Good. Then finally, after you insert your objective aperture, you want to check for the astigmatism of the objective lens. So here we're moving the objective stigmator, and what we look for here is the difference in defocus along the x and y axis. So when you have astigmatism, just like I showed you for the condenser lens, you will have a difference in strength on the lens, and the focus in one direction will be different to the focus in the other. You can interpret this easily if you do an FFT of your image. Here's an example of an astigmatic image with an oval FFT, because the focus in this direction is different to the focus in the perpendicular direction. Once you correct for it, the focus is the same on both axes, and you have a stigmated objective lens. Good, so I made a little video to show you how to do this, all these steps on the Cryos. And I'm playing this video at 2 times, so we're not here all day. So it'll be twice the speed that you would normally operate. Okay, so first step, put your sample in, adjust the eucentric position. That brings the specimen to the same height every time, so you don't get different magnifications from session to session and from area to area. So to do this, find an area, a feature like you do here, and then change the z-axis by 10 or 15 degrees. If you're not at eucentric height, the image feature will move away from the screen, and you bring it back using the z-axis. So that's pretty simple. Repeat it a couple of times until the object stays centered. Click eucentric focus at the end. This is just a preset for setting the objective at focus at the eucentric position. Next thing is to center our C2 aperture. Now you see what's happening here. On a normal microscope, a non-Cryos microscope with 2 condenser lenses, we don't have this issue, but the Cryos has 3 condenser lenses, and in effect what you get when you expand the beam and you contract it, you get a little bit of a swing when the 3rd condenser lens kicks in. So when you're going, you can't read here, you're going from convergent beam to parallel, you will get a swing. So what you have to do, you have to disable this third condenser lens in order to do this alignment properly and make it more like a Techni microscope. So what we do is we go into free control and turn the third condenser lens off, and now we've got a Techni microscope with just 2 condenser lenses. To center the beam, go to crossover, so make the beam as small as possible, shift it with your deflection coils to the center of the screen, and then expand it. If the aperture is not centered, it will shift to one side. Activate your adjustment feature and then recenter mechanically using the multifunction X and Y. So check it a couple of times, and once you're happy, remember to click on the adjust again to disable it. Eventually you will get a beam that expands nicely and concentric with your viewing screen. Don't forget to then go back to normal TEM mode and enable the third condenser lens, otherwise you will not have a parallel beam. Condenser lens stigmation, it's important to do this at the spot size you're going to collect data, because changing spot size affects the astigmatism of the beam. So in this case we were collecting at spot size 9, which we've changed at the bottom. And we go to high magnification that allows you on a FEG microscope to really see your source very clearly and really judge whether or not you have astigmatism. So what we've done, we're going to higher mag here, and you can really see the astigmatism now. Go to your stigmators and activate them for the condenser and use multifunction X and Y to make the beam symmetric. Then check again, go back and forth crossover. If the beam expands nicely without changing shape, you've corrected your condenser astigmatism. Direct alignments. So here it's important that you do these close to focus, because they're dependent on the objective lens value, and that you do them ideally in the illumination conditions you're going to collect the data at. So the spot size and the C2 intensity that you're going to use. Also, if you're using TM or FTEM mode, stick to those modes so that you can, because they do change if you switch between them. So in this case, I'm going to show you how to do them in FTEM mode, because we were going to use the K2, but I'll also switch back and show you how to do them in TEM mode. You just have to do them in the mode you're going to collect data in, not both. Okay, so here we are. We're in FTEM mode now. And the first thing is to focus. So we want to focus the specimen so that we're working close to focus. So we switch to the Gatan PC and change the focus knob. And to focus, you just look at your first 0 here in your FFT and then bring it out to the edges. The contrast in your image should also disappear once you're there. And now you're to focus. Same thing now, doing it on the flu screen in TEM mode. So here you don't need an FFT, you can go by the fringes in your image. So you can see the fringes from over focus and go back until you lose these fringes, then you're in focus. We're back in FTEM mode now. We want to do our direct alignments. Beam shift just centers the beam, that's all it does. It just resets the beam to the center of the screen. Then you do the nanoprobe beam tilt pivot points. So what you're doing here is you're adjusting the beam deflection coils so that when you do a tilt, you're not shifting the beam as well. So what you're doing here, the beam is, the microscope is tilting the beam very rapidly, and what you're doing is making sure the pivot point is on your specimen. So you make those 2 points the same. The next step is the rotation center that I talked about. So this is making sure now that the beam goes parallel to the optical axis. So the microscope is going to start wobbling the objective lens current, and you're going to see things in the middle of your screen starting to move, and you just want to reduce that motion. So we've clicked on rotation center here, and we go somewhere where there's a bit of contrast, so the edge of a hole here, and I had to induce a rock here because actually it was fine. And there we go. Once you're happy with that, you can finish. So we've adjusted the rotation center. The next step is to do it even more accurately using the comma-free method, which I told you. So you have to go back to your CCD camera now, and you're just going to use multifunction X. You don't need to use Y. And the microscope now is tilting the beam back and forth a certain amount. So you're actually getting two images. In this particular video, it doesn't show up great, but you can maybe you'll be able to see that you're getting two different defocus values. And you just have to adjust multifunction X until the alternating FFTs look the same. This will show up a little bit better in TEM mode in a second when I show you this. So in TEM mode, same thing again. Go to direct alignments. We've already focused. We do the beam shift, then the pivot points. Actually here they were quite bad. So bring those two spots together. Do the same for pivot point Y. Good. And now the rotation center. So it was quite bad here. You can see the middle is shaking quite badly. So we just adjust multifunction X and Y here until the image stops wobbling. Good. So then we switch to the CCD camera and select the theta here so we can look at the tone rings to do the comma free. So here the rotation center wasn't perfect. So you're going to see the difference. The comma free was actually a little bit off. So you can see the two FFTs are quite different. And then gradually, as we adjust multifunction X, they start to converge. Then go to Y, because if Y is bad, it also affects X. So go back and forth a few times. So eventually, we've got them to where they're looking the same. Now, there is automated software now. I think Cryo-EM can do these procedures automatically. And when you have a faceplate, you get this software called AutoCTF that will also do astigmatism and comma-free automatically for you. But I think it's still nice to be able to judge what things look like when they're bad, even if you do it automatically. Good. Centering the objective aperture. So we're doing this in TEM mode now. So you have to go to diffraction mode because the objective aperture is close to the back focal plane of the objective lens where the objective aperture is. So we're centering the diffraction spot here just because it was a bit off-centered. And you might have to adjust the intensities, the gray levels manually in order to see. We've just inserted the 70 objective aperture, and then you adjust the gray levels here, and now you can see the outline of the aperture. Also adjust the intensity. This can help clarify the shape of your aperture as well. And now you can see the central diffraction spot in the middle. You want to center the aperture around the central diffraction spot. Okay, then click adjust again to disable multifunction X and Y. In TEM mode, same thing, go to diffraction mode, center your beam if you need to. Insert the objective aperture, adjust the conditions here, and then center it. In this case, it looked pretty good to begin with. Finally, objective-less astigmatism. So what we're looking for here is to make the tone rings nice and circular so that the focus in the X direction is the same as in the Y direction. It wasn't too bad, made it a little bit bad so you can see. It is better also to do this as close to focus as possible because you can really see the astigmatism clearer when you're close to focus. And some people take ages to do this. It depends how accurate you want to do it. I think a little bit of astigmatism is okay in your images since the software also deals with it. Right, then you can take a full image at the end and do an FFT with 1 micron defocus and just check that it actually looks good. And showing the same thing now in TEM mode. Pretty much the same thing. You can use your CCD camera or your theta to adjust the objective astigmatism. So, 9-minute video sped up 2 times, it should only take you 20 minutes to do your alignments. Cool. Good, so we'll move on now. Move on from alignments. Good. Choosing the right microscope. So this depends whether you're doing screening or if you're doing data collection. I wanted to talk a little bit about screening because the best screening microscope, Chris said, is a Cryos. And it is. It's easy to use, easy to load lots of samples, but we don't have access to a screening microscope like a Cryos. Well, we do, but we shouldn't be screening on the Cryos. So we use the lower end microscopes. And for this will be affected by the type of gun that you use. So whether you use a thermionic or a field emission gun. So if you have something big, you'll be able to see this clearly with a thermionic gun. So shown here are some 26S proteosomes taken with the focus of 2.5 on a spirit with a CCD camera. And you can see the particles quite nice and clearly. In fact, when you compare it to an image from the Cryos, they look more contrasty. This is due to the lower kV. Now, if you look at the FFTs of these 2 images, you can see that the thermionic image is actually, there's no information beyond 30 angstrom. And this is to do with the coherence of your source. Whereas on the FEG, you visibly have rings going out to at least 3.9 angstrom. So this is not a directly fair comparison because we are using a direct electron in the one microscope and a CCD camera on the other one. But the biggest effect here is not the camera, it's actually the source of the gun. I'll show you some more examples now. So large things show up nicely, even if you're using a thermionic gun. Go down to smaller things. This is lysinin, about 300 kilodalton. You can see on the FEG, you have nice particles. You can tell orientations. You can see internal details. Again, this is the K2. But if you look at it on tungsten, you can see the particles, but they look kind of fuzzy. You can't really see internal features. So it's still usable at this size range as long as the sample is actually behaving and it's not falling apart. You can see things. It's when things don't go right that you can have problems with a thermionic source. If we go even smaller here, this is a 80 kilodalton protein that Chris Hill is working on. And you can see the images on the F20. You can see the particles clearly. You can even make out a shape. Whereas on the spirit, it's kind of hit and miss. You can't really tell those are particles or is that your eyes, dirty eyes, or the background. So just to show you that it's not just the camera here, here's an example of a protein that I used to work on, taken on F20 with a CCD. This is before direct electron detectors. This is a 200 kilodalton toxin. You can still see the particles. You can see features. So the big difference there is due to the gun. So for screening, if you can get a FEG, that will make life easier for you. However, if you're looking at large things, so I would say anything above 500 kilodalton, you should be able to see it easily on a tungsten microscope. Problem comes when you look at smaller particles. And the problem comes when you're troubleshooting. Is your concentration not right? Is that why you don't see things? Is it falling apart? You don't have the contrast and the resolution to see that when you're using a tungsten microscope. Now, a few people here, Richard and Chris and Greg, are working on developing, or at least working with companies to retrofit tungsten microscopes with FEGs so that we can have affordable screening microscopes. Greg is working with people to develop detectors that will work at the lower KVs and produce nice images. So hopefully soon we will have a nice, affordable screening microscope that will give us really nicely interpretable images that we can take to the Cryos. Right. Before I talk about choice of microscope, I think we need to talk about detectors because the detector is almost as important as the microscope to some extent these days. So Chris talked about the detectors. He showed Greg's curve here. And you can see here the DQE, which is the measure of degradation of signal against different spatial frequencies. They all start up relatively high at 0 Nyquist, and then as you go towards Nyquist, they all fall off, but they fall off to different amounts. They're all better than film, and what you see here is that the counting detectors, such as the Falcon 3 electron counting and the K2 Summit, actually have higher peaks at the lower spatial frequencies. And this is important. These low resolution features are important, especially for small particles that exactly don't scatter much. So you don't have much information for aligning there. So choosing a detector, if you're looking at small things, it would be advantageous to use a counting detector. Now the big particles also use the low frequencies, but they scatter quite a lot, so you can actually see and align these things properly. Now, I'm not going to tell you which one to choose. I think you just have to try and decide for yourself which one you like. The data is there. We're getting good results with the Falcon as we are with the K2. But I'm going to talk a little bit more about them now. So the integrating detectors, such as here the Falcon 2 and the D20, so they work differently. As an electron enters your chip, the signal is scattered, and you get an integration of the signal over several pixels. And this causes noise due to the random nature of deposition of energy by the electrons and the readout noise. And generally, you have a lower DQE in these images. However, there are advantages. You need shorter exposures, and you can work at higher dose rates. So those two things work together. So you can take faster images, take more images faster. Now, with the counting detector, these events that happened here are reduced to a single pixel. But in order to be able to do that, you have to either have a very fast frame rate or a really low dose rate. And it's the equivalent of being able to count drops of rain as they fall on your sidewalk. So shown here is when you have just a few drops when it starts raining, and you can actually count the events. However, if it starts raining really fast, you can't distinguish the events. So this means that we have to have very low dose rates, so anywhere between 0.5 to 5 electrons per pixel per second, and we have to have very fast frame rates. What this means is that we end up taking longer exposures as well, which affects the data collection. However, the payoff is that you get less noisy images. Now, some of these detectors, such as the K2, is capable of further reducing the events and sublocalizing the events to inside a pixel. So this is called super resolution mode. And there's an advantage to super resolution mode in that you can reduce the aliasing at Nyquist. So there's noise, there's information in your images beyond Nyquist. And that information actually gets aliased back because it's undersampled back into your image, which then looks like noise. So you can get away with that noise if you take a super resolution image and process it as it is, or if you Fourier crop it, and you can reduce this noise at Nyquist. However, keep in mind, what is your Nyquist, and do you really need to be at that resolution? For example, at 105,000, Nyquist is 2.3 angstrom. And I think we'd all be happy with that resolution, but more realistically, our reconstructions probably go normally to 3 and 3.5. So do we really need to preserve those frequencies right there? Furthermore, as you can see, the decay on a detector like the K2, the information past Nyquist is not significant, so you wouldn't be gaining that much. Furthermore, if you decide to collect in super resolution mode, it will slow down your data collection, and you'll have bigger file sizes to deal with. There was a recent discussion on Twitter, so this is unpublished data, but Rado Danev took one of his super resolution data sets of the 20S proteasome, and he compared the resolution by processing the data in super resolution and then by real space binning it instead of Fourier cropping it, which is the equivalent of doing counting. And you can see the difference was very, very little. It was 2.4 angstrom for the super resolution data set and 2.53 for the counting. So you need to consider whether or not it's worth it. Now, yes. So let's talk a little bit about the characteristics of each detector. The Gatan K2 summit runs at 400 frames per second. It will output at 40 frames per second. The optimal dose rate is anything below 5 electrons per pixel per second. And we usually take exposures of 8 to 16 seconds. Here's a typical setup. It would be a good starting point. At 105,000, where our pixel size is about 1.15, this dose rate is equivalent to 3.8 electrons per angstrom square per second. And that will, a 12-second exposure will give us 45 electrons, roughly, in total, which is a good amount. Then the Falcon 2 collects at 17 frames per second. It only does linear mode, so this is what we had on our 2 cryosys initially before we upgraded to the Falcon 3. We still got very nice data, a lot of data from these detectors. And the optimal dose rate is 2 to 3 electrons per pixel per frame with typical exposures of 1 to 2 seconds. So we could take a lot of images with these detectors per hour. So another example, at 59,000, this dose rate, you aim for about 29 electrons per angstrom square per second. Then the Falcon 3 is faster, 40 frames per second. It can do linear and counting modes. And Greg promises us, he's working on it soon, he'll be able to do super resolution. And because the signal on Nyquist on the Falcon 3 is higher, you'll be able to get more useful information from these super resolution images. The dose rate for linear mode is the same as the Falcon 2, but for counting, you need to drop the dose rate real down. 0.5 to 0.7. If you ask Greg, it should be 0.5 to 0.5. So typical exposures are, again, a couple of seconds for linear mode, and for counting mode, we typically use 60 seconds. So I'll just concentrate on the counting condition here. We typically collect at 75,000. We've collected at 0.6 electrons per pixel per second with good success. And so typically a 60-second exposure at that magnification will give us about 31 electrons total dose on the sample. Good. So now we can go and ask ourselves, data collection, which microscope to use? Again, the answer is get the best microscope that you can. Ideally, a 300 kb with a direct electron detector. So there are other things that influence such how good the vacuum is, the contamination rate, ease of use, all these factors have to be taken into consideration. Here at the MRC, we have a very nice Polara, which has a Falcon 3, which only runs in linear mode, but lots of people have got very nice data from here. There are about 32 sub-5 angstrom structures deposited to the MDB from this microscope in the last 4 years. Typically, the samples that we go here, because it's in linear mode, are the larger samples, so anything above 500 kilodalton, although some people have gotten below that as well. Polara 2 will be coming soon. It's in storage in one of our rooms here, and we're hoping to outfit this with a Gatan detector. Then Cryos 1 is equipped with a Falcon 3 electron counting and a Quantum K2. Cryos 2 the same setup, but it also has the Volta faceplate. So again, get the best microscope you can get with the right detector for your specimen. Good. So let's go into checking our grids now before we set up for data collection. So it's important to look around your grids, because even though you've frozen your grids and you've frozen 4 the same way, as you know from experience, these grids can look kind of different. So easiest way is just drop the mag down, drop the magnification down, and look around your grid. Alternatively, you can do an atlas if you want, but an atlas will take 10-15 minutes, and it's just really easy. Just drop the mag, spread the beam, look around your grid. Does it look interesting? Is it worth staying on this grid and looking for squares? Then to find your good squares where you have particles, use the low-dose software, which I'm going to talk about in a second. It's really easy to use and very fast. Then just save the coordinates that you like in your interface to go back later. So here's an overview of what a grid looks like. This is an example of a nice grid. So you have areas that might be a bit too thick up on the top. This might be a bit too thin just from first observation. And then hopefully somewhere in the middle, you have the ice that's suitable for your sample. Now, here's another grid. So you can see what's happened here. Not a big deal. You've got where your tweezers were. So that's destroyed all the squares in that area. But there's still lots of usable information. Then, here's another grid. So would you collect on this grid? Take a look. It doesn't mean that it's totally useless. You only need 5 to 10 squares for a data collection. So don't discard this grid, especially if you spend a long time purifying your product and only have a few microliters to play with. Just take a look. You might have something that you can work with there. Right, so what is good ice? Finding good ice. The image is a little bit overexposed there. In general, as a rule of thumb, I tell people find holes where the gray levels in the holes are lighter than the carbon that surrounds them. So in this case here, you can see these holes, unfortunately didn't render very well, but you can see that there is good contrast in the holes. If we look in the thick ice image, especially in the middle, you can see that the holes are actually very hard to distinguish from the background. This is going to be too thick to collect on. There are holes on the edges here that could be suitable, but in general, this square would be too thick and not ideal. Even on this grid, always try and avoid the edges. The edges is where you will find a lot of crystalline ice. So we generally just don't pick any holes there. Good. Now, thin ice is good, but at some point you can get too thin. And this is the image that Richard showed in his talk. This is what the hole would look like at low magnification. So you have a ring of thick ice, and then in the middle it gets really thin. And there's 3 things that can happen when the ice gets too thin. You can exclude your particles, like you've done here from the middle. You can have preferential orientation because the molecules lie on the air-water interface and in the thinner axis. Or what a lot of times happens is that the complexes just fall apart, or your product denatures. So thin ice is good up to a point, and then it can be bad for your grids. Now, if you use carbon, a lot of people use carbon as an extra support over their grids, especially when you're looking at something big. It can be quite nice to use carbon. Ribosomes, proteasomes, most of the somes which are big, actually, you can use carbon. They look different though, and don't be put off. You'll see, a lot of times, you'll see a more uniform spread of ice, so you won't have this sort of lens effect in the holes. And you might see the shadows in your holes. And I was put off by this initially when I saw my first grid with carbon. And then somebody more experienced came and said, no, this is the good stuff. This is where you want to be. So what you're seeing here, the shadows, are basically, we think, wrinkles in the carbon, and then you get these mountains and valleys where some of the water stays and creates thicker ice. But this is usually where you find the nicest particles. So this is true for ribosomes, it's true for spliceosomes. I know that when Kelly was doing her spliceosome structure, the spliceosomes would like to accumulate in the sort of the interface between the thin and the thick ice, and that's where she would use to collect images. And you can see the little ribosomes here, which are quite visible at this magnification. Then ice appearance with graphene oxide. Graphene oxide is becoming really popular, and when you look at your grids with graphene oxide, you might say, wow, this looks really dirty, it looks messy. Maybe I didn't make a good grid, or there's something wrong with my ice. But this is what they look like. They look a little bit messy. And sometimes you can even see big flakes of graphene. But in general, what you're going to see, again, kind of uniform ice, but it will look messy in the background. You'll have this kind of smudges. Now, when it looks too clean, it could mean that you don't have good coverage of graphene. For example, you can see here the background looks just too clean. There's just ice there. And we took an image in this hole and this hole. So here and here, and you can see here we had no particles, here we had the particles. Good. Look out for crystalline ice. The causes of crystalline ice, there's several factors. When you're freezing your grids, if your ethane is not cold enough, it means that you won't freeze fast enough to get vitreous ice, you'll get crystalline ice. If your grid handling is a little bit sloppy sometimes, if you don't cool your tweezers long enough, you may end up warming your grid during the transfer. If you crash the vacuum in the microscopes, rarely, but sometimes, the holder temperature at the tip, because it's not cooled directly, it's cooled indirectly, will warm up. So these are some of the causes. And like I said, avoid the edges of the grid squares. So how can you tell crystalline ice? When it's really bad, like when for example, you haven't frozen fast enough or the cryogen temperature is low, you'll see the stripes in your ice. And then when you tilt the stage, the stripes will sort of sparkle and disappear and appear. So just when you're doing your wobbler and setting the eccentric height, if you start seeing these lines appear and disappear, you know you've got crystalline ice. So change the grid or move to a different position. At higher magnification, it'll be very obvious. You will see an ice ring at around 3.6 angstrom, and your background will be quite dirty. You won't be able to see your particles. So this is really not usable. Good. And the end result, you want to have something that's good concentration, nice ice, something that looks like this that Rebecca collected, and she collected all of these data sets. But just to show you that this data set, this micrograph came from that grid that wasn't super perfect. So don't judge a grid by its atlas. Good. Right, so you found a good grid now, so you want to collect your data. What are your choices? You can do it manually with the FEI low dose. You can use semi-automated ways, or you can go fully automated. Now, there are several packages out there. I'm going to concentrate on the ones that we use here at the LMB and we have some experience with. But these are the main ones, but there are more software packages from different companies and different labs that allow you to collect data. So the low-dose software has been around for a long time, and this is actually how everybody used to collect data before these automated software packages came out. It's pretty simple. You have 3 modes: search, focus, and exposure, and each mode is basically a preset for your optics, your magnification, your intensity, your spot size. And that's basically it. When you click from one to the other, the microscope just changes the illumination conditions and your magnification. You have 3 modes, and typically your search area will be a large area. You're working at low magnification, and the idea here is just to find a suitable hole for data collection. Once you've identified a good hole, you then switch to focus mode. In focus mode, in order for you not to burn your sample, the microscope does a clever trick. Over here, it shifts the beam onto a neighboring area. In this case, it's the carbon in between the holes, which we don't care if it burns. So what the microscope does, it uses the beam deflection coils to create an image, a beam shift, which is shown here. Now, so basically, this is the hole of interest, for example, and this would be the focus area. Now, if this image continued down the optical axis, it will be formed somewhere here. So the image deflection coils move the image back into the center of your screen. Collectively, it's called an image beam shift. So your focusing occurs here, and then once you focus, the beam comes back down to the optical axis and collects an image at whatever conditions you specify here. It usually, the speed is maybe, depending on how you do this, 1 or 2 images per minute. So some people here at LMB were really fast at collecting data this way. Good. Then the semi-automated ways of collecting. An example is UCSF image 4 from Yifan Cheng and David Aggart. This is an interface basically for controlling the FEI low dose routine. So it allows you to basically go from hole to hole in an automated way and run through search, focus, and exposure. So you don't have to sit there and do this manually. You just set up a a grid square, and then center a hole maybe at the top left of your image, and then let the microscope go in a pattern and collect data. This worked okay if your holes looked nice. If they were messy, it wouldn't center the hole sometimes. And also you kind of walk away for a long time, because after a couple of hours the grid square would be finished, so you have to set up another one. So then things got automated completely, and that was a great day for electron microscopists everywhere. And there were labs. The Legion software was already running years before EPU showed up, maybe 10 years before EPU. But we got hold of EPU when we got our new cryos, and it's really nice software. EPU stands for out of many more in Latin, meaning out of many particles you get a single structure. The software is very user-friendly. Basically, you make an atlas like you do, then select suitable squares, select the holes inside the squares in a manual or automated way based on the gray level of the holes. Set up your exposure settings, so you set up your illumination settings here, and where you're going to do your focusing and tracking, and then you start data collection. Okay, we have manuals for all of these on our website, how to use it. Then, so EPU is actually very easy, and it's reliable. It's not just easy to use, it actually runs very reliably. Usually it will stop if there's a user error, so if the user didn't set the eccentric height properly for a square, it will stop, or if there's a problem with the camera or the microscope itself. Otherwise, it's pretty reliable. It works now also with the K2. Initially, it only worked with the FEI detectors. And the newest versions are also compatible with the faceplate. So you can switch faceplate position and also offset the beam tilt. These are the speeds that we get when we collect single images per hour. So, okay, then we have Serial-EM. Serial-EM was written initially for tomography data collection, but then scripts were written for adapting it to do single particle. Scripts from Shen Chu and Wim Hagen, mostly. And there's a library now for sharing scripts for Serial-EM at this website here. Again, the user sets up a grid map or an atlas, selects the good squares, and then collects more images of those grid squares. Then you select the holes. The hole selection is done a bit differently. Instead of going by ice thickness, you basically create a lattice of points with defining 3 corners of the lattice and the distance between the holes, and then it'll automatically set the points in your holes. You can also manually add or remove holes. Serial-EM is free. That's a big plus. It's very flexible and customizable, and there's great support from David Mastronarde, who developed this software. And even you can pay a bit of money to support Serial-EM, but even if you don't, there's a Serial-EM discussion group, and David often replies within an hour of asking a question. It works with the K2 and the energy filter. It will start working again with the Falcon once, because FEI changed the way they save the frames. It stopped working. David is working on a solution now. It can compress the files that you're saving, so saving space locally on the microscope. And it does some anti-aliasing filtering to reduce the effects of aliasing in your counting images, so that could be an advantage. It's a bit faster than EPU as well, at least with the K2. And it works on other microscopes, not just FEI. And like I mentioned earlier, it actually has new routines for doing autostigmation and autocoma that can be quite useful. Good. Just to finish off quickly, charging. Chris talked about it a little bit. This happens due to the insulating properties of our sample. If you put carbon on tomography, this can reduce. Happens when the beam hits your sample, electrons are lost, and you create local positive patches which act as a lens. And this will show in your image as a smear, but not a uniform smear. So you can see we still have sharp particles here, but it's charging in that part of the specimen. And if you look at your FFT, it will look a little bit like this. So how do you avoid charging? There's been some studies done, including here at the LMB, so symmetric illumination in your specimen can help with this, and contacting the carbon symmetrically around the hole. And using an objective aperture, backscattered electrons will go and supplement and stop the charging. Objective aperture is useful for other things. It gives us a little bit more contrast. And check always after you put the objective aperture in that your astigmatism is okay, because it affects it. Chris mentioned that the aperture will cut off your resolution. Keep this in mind. On the cryos, on our cryos, if you use a 30 micron aperture, you won't get below 4 angstrom. I think we're okay for now with the 70 and 100. Good. What magnification should you use? This depends on your experiment. But if you consider that at lower magnifications you get more particles, you have to think about your experiment a little bit. Is it a sample that is guaranteed to go to high resolution? Have you done some preliminary work? Then by all means, cramp up the magnification and try and get to high resolution. If it's an initial study, you're not sure if your sample is homogeneous enough, or if you've got a variety of different conformations, it might be good to drop down the magnification and collect more data. So, and remember, when you choose your magnification, as Chris suggested, don't forget to set the eccentric height, because this will affect the final magnification, your final pixel size. And if you can collect an image of a gold grid, or just an image of your ultra stable foil if you want, so you can calibrate the pixel size more accurately. Good. What defocus range to use? For most projects, generally we go between 1.5 and 4 microns, with about 0.3 micron intervals. In counting mode, because of the higher signal to noise, you might be able to see the particles a bit better. Always check your images after you start collecting, not just to see if you can see the particles in the low defocus. Make sure you don't have any charging, any astigmatism. Just take a look at your data after data collection. Don't just walk away, because something bad could be happening and you're just going to collect rubbish in the end. Another consideration for smaller particles, it might be advantageous to put more dose to boost those low frequencies, and then you can deal with the radiation damage later in RELION. Good. This is just some characteristic defocus spreads in EPU. We selected 3 values here, and you can see that we've got 3 islands of defocus. However, they do deviate from the selected defocus by about 0.15 microns. So it's not necessary to do very fine or very small intervals for your defocus, because the accuracy is not that great. If you don't focus at every hole, you can see that you get a more uniform defocus, but you can also get things that you don't want. For example, here, about 400 micrographs were collected at a defocus which we didn't ask for. This is probably because the grid was not completely flat. So a little bit of a non-flat grid will result in the height changing as you move along the holes. So keep this in mind. Good. This is an example in serial EM as well. All right, to finish off, the final thing I want to say is that if you're looking at small complexes, this new faceplate technology might be advantageous. We've started testing it here at LMB. There's a few people here that actually have some really nice results. This is a test we did on lysine with Rafael Eiro from Minder's group, and we actually, without really much trouble, we got to 3.9 angstrom from 5,000 particles when we were initially testing it. So it holds great promise. People like, hemoglobin at 60 kilodalton at 3.4 angstroms. It's very exciting to have this technology. It's fairly simple to use for single particle. All you have to do is set up this in-plane condition so that your beam is parallel and that it crosses the faceplate in a single point. For tomography, you have to do a few more things because you're shifting the beam for tracking, and you don't want to induce a tilt while you're doing the shift, because that will create a satellite spot on your faceplate and affect the potential here. Good. With that, I'd like to finish and thank the people in the EM facility and all of the LMB and Jake and Toby as well. Jake and Toby don't just help us with the processing and with the servers, they help us when, you know, when I go there and ask them, do you have a hard drive for a microscope? How do you do this? So they're really helpful always. So we have more movies actually, they need a bit of editing, and there's going to be instructions on how to do EPU data collection, setting up the faceplate, GIF tuning, and doing gain correction and all that. So thank you very much.